Hi everyone, this is your struggling CS student here. Today let's solve another LeetCode weekly premium problem. So let's take a look at today's problem. Find the closest mark node, okay? So you are given a positive integer n, which is the number of nodes in a zero index directed weighted graph and a zero index to the array edges, where edges of y is u, v, w indicates there is an edge from u to v with weight w. You're also given a node s and a node array of marked. Your task is to find the minimum distance from s to any of the nodes in marked. Return an integer denoting the minimum distance from s to any node in marked, or -1 if there are no paths from s to any of the marked nodes. Okay, let's take a look at some examples. N is 500, 10 to the power 4. The graph might have repeated edges. The graph generated such that it has no self-loops. Okay. So n is equals to 4, and these are the edges. And mark is equals to s and 3, and you're starting from 0. So the output is 4. There's one path from node 0 to node 2, which is 0, 1, 2, and has a distance of 1 plus 3, which equals to 4. Okay, and there are two paths from node 0 to node 3, which are 0, 1 to 3 or 0 to 3. Now the first one has a distance of 6 and the second one has a distance of 4, and the minimum of them is 4. Say a -1 example. Answer is 3, answer is 1. Okay. There are no paths from the node 3 to any of the marked nodes, so the answer is -1. Okay. Your task is to find the minimum distance to any of the nodes. Okay, so return an integer denoting the minimum distance from s to any node in mark, or -1 if there are no paths from s to any of the nodes. Okay, understood. Now I was a little bit confused, like what if inside of the marked nodes, your source node can reach one of them but not the other? Then in that case, my understanding from the problem description is that you'll just return -1 because, wait, no, that's not true. Okay, I think as long as you can reach a node, then you should have an answer, right? Let me check. Let me check my understanding. So let's take example 3. Let's say the mark node is 2 and there's an edge from 3 to 2, right? So edge, an example here where you have 3 to 2 of 2, and then in your mark nodes you have 0, 1, and 2. And the answer would be mark plus s. Wait, what? I expected mark plus s to have a size of 1 to 3, but got 4. Or is it because of that edge constraint? Okay. Wait, not this. Not this either. It's the edges dot length. This one. Or I could be wrong actually. Let's say we remove the 1 and 2. 1 to 2 with a weight of 3. Mark plus s. Mark plus s. Okay, maybe it's like this. Let's restore this. 1 to 2 with a weight of 3. We have 2, even though okay. So even though from here, right, as long as you can reach any one of them, then we want that as the answer. But if we can't reach any one of them, right, yeah, there are no paths to reach any one of the marker nodes, then we return -1. Okay, understood. So initial intuition is we can use Dijkstra's algorithm from our source node to the destination node. And yeah, our source node is always fixed. So not sure if Dijkstra is good enough because how big is Mark? Ooh, Mark is quite big. Because if we do something like for each node in Mark, we run Dijkstra's, right? Dijkstra of source to node, which is the destination. Maybe I should call this destination. For each destination in Mark, we do this. What's the time complexity? Time complexity of Dijkstra is v plus e plus v e log e. Okay. Oh, v plus e log e. Yeah. This is the time complexity of Dijkstra's. Or maybe it's just like this. And then you need to take Mark times this, right? If we're doing Dijkstra's. So Mark can go up to, how big is Mark? N minus 1. So it's 500. 500 plus 500. Is it 500 pages? No, pages is 1000 log base 2 of 1000. Is this good enough? Mark can go up to v actually, basically. So then we have v squared plus v times e log e. 500. I think that should be fine actually, because it's if n is okay, I should put here as n actually. If n is 500, then I think n squared algorithm should be fine. Should be fine. Okay, I think we can just do that. Wait, actually? No, what I'm talking about, we don't even have to, no, we don't have to do this. Oh my god, I'm trolling. We don't have to run Dijkstra's from the source to the destination. We just need to run Dijkstra once and we should be good. Yeah, oh my god, trolling. Then in that case, this is time complexity. N plus e log e. Yeah, where n is the number of nodes and e is the number of edges. And then this will definitely pass. So we just run Dijkstra on the whole graph and we can create in one time basically. Yeah, okay, let's do it. So source node we already have. Let's have something like distances. Let's do run math import infinity. Distances is infinity times n. Then we have distances to the source is equal to 0. We definitely have a heap with a cumulative distance initially of 0, then node s. Then what else? We have a visited as well. PC. Oh. Okay, we have a visited equals to set. What else? Is that all? Let's watch on ahead. Distances visited. Oh, I remember now. Yeah. Okay. So we do node is equals to heap hop of the heap and import some stuff. Here import heap hop and push. So this is just standard Dijkstra's. Actually it's the distance, current distance, and the node. So we say if the current distance, or rather if the distances to the node is less than current distance, then we can just continue. In essence, what this code is trying to say is that if we reach this node, but we've already found a better path to that node, then we don't need to continue processing the current edge in essence. And we say visitor.add node. But then now it's the case where we actually find a better cumulative distance than the distance we took originally reach a node. Then we want to explore down that path. So now we mark the current node that we are visiting as visited. And for neighbor, well, I just realized that we actually have to build the graph. So that's a mistake on my part. Was default date from collections import default dictionary. So default dictionary just how should I say, sets a default value provided by the function. It is passed into the constructor when you set a key. So what I mean by this case is if you set some sort of key here, right, then immediately if the key doesn't exist, it will set it to an infinity select. So it allows us to do shorthand or something, or immediately using the data structure that's being hashed to the key. So I hope that makes sense. All right, so for UVW in edges, actually, we actually might not need a default date. We can just use a dictionary comprehension for I in range of n. Okay, that's because we already have the number of vertices that is marked from 0 to n minus 1, right? It has to be? Okay, good. Then graph of u dot append v w. Now we have the graph setup. Now we can use it here. So as we reach a node in our Dijkstra's algorithm, we will check for each neighbor. For neighbor with in graph of node, then we will calculate the current distance, or rather the cumulative distance so far. We say distance is equal to current this plus the weight. If the distance is less than the distances to our neighbor, then we want to update it. In essence, we only take the edge if the cumulative distance that we have so far and plus the weight or the cost to reach our neighbor is less than what we have already recorded, then we want to continue exploring down that path. Otherwise, there is no need to explore down that path. So distances of name is equal to this, and we push it the distance and the neighbor. Right. So okay, after I believe that is it for Dijkstra's algorithm, unless I made a mistake. So current distance node distances to the node. If less than, yeah, then we continue. Else, actually I forgot to add something. If the neighbor is already seen, then we can continue. Yeah. We already visited the neighbor. There's no need to visit it again because Dijkstra's work in a greedy manner in which the first time we reach a node is also the most optimal path to reach that node. Okay, so let's see. I'm trying to see if I'm if I went off a tangent. Okay, I'm not. Okay, there's no negative edges. If there are negative edges, then Dijkstra's would not work. Actually, I've checked that before. But yeah, anyway, we only have positive edges, so Dijkstra should work here. Then now for destination in mark, we would check, right? Say best equals to math.infinity because we want the minimum. So in mark, if the distances to the destination is not equals to math.infinity, that means we've reached that before. We'll say best equals to min of this distance as distance. Then we will say return best if best is not equals to what happened there? Math.infinity else negative 1. I think that should be it. So basically, if we didn't manage to find any of the we didn't reach any of the vertices, then distances of destination in mark will always be equal to infinity. We will never update best. In that case, that means we couldn't reach any of the nodes in mark. So if mark is equals to math.infinity, we return negative 1 as stated by the question. Else we return best because we actually find a pair. Oh, seen, did I? Oh, I used visited. Sorry about that. So, okay, it looks like past the sample test cases. I think it should work. Let's space complexity is O of B plus E, n plus E. Yeah, where n is the number of nodes, and E is the number of edges. Okay, so like this. Am I confident? I think I'm confident. Yeah. Okay, let's go. Okay, accepted. Nice, very good. I'm gonna erase this. Just take a look at the editorial real quick. Yep, Dexter's algorithm. Nice. It's just a direct application. And let's see the time complexity. This is the V plus E log V. Well, you can get this time complexity if you are using a very efficient heap called the Fibonacci heap. But since I'm just using the off-the-shelf heap, then it's possible that the heap contains up to it can contain all the edges, or like in the worst case, if you are just using off-the-shelf heap, right? Like I'm using Bellman-Ford algorithm with non-negative values. Yeah, or we don't have negative. Okay, okay, yeah, sure. But I think Bellman-Ford, it's the time complexity is not as good as this. It's not as good as Dijkstra's. Yes, n times n, shortest path, faster algorithm. This is an optimization. One idea from. Oh, interesting. Okay, okay. It's still n times m. Okay, but maybe the average case it's better. Yeah, I didn't learn Bellman-Ford. Oh, there's no comments. Oh, what the hell? Interesting. No comments. Oh, yeah. Anyway, I haven't learned Bellman-Ford. Dijkstra I did learn, and for in the context of interviews, Bellman-Ford is definitely uh, less well known. Not less well known. Sorry, it's less likely that you'll be tested on Bellman-Ford. But I think it's still good to know Bellman-Ford, because if you're given a graph problem during an interview that has negative edge or negative edges, then that is like a tool in the toolkit that you can use, right? For me right now, the only tool that I have with regards to shortest path problems is Dijkstra's. So definitely Bellman-Ford is something I should learn to improve or expand my toolkit, right? Anyway, this is the solution to the problem. Just share again here real quick. Right, so we built the graph first, then this is Dijkstra's algorithm, right, using a heap. If you don't know Dijkstra's algorithm, then I suggest you go go online, go YouTube, take a look. Afterwards, we just in O1 time check if we are able to reach the node or not, and if we did, we just update the whatever the question wants us to return, which is the closest marked node. Anyway, that's it for me. Thank you very much for watching, and have a great day ahead.